Hello. Today we're going to talk about nowhere differentiable functions. First, let's do a quick review of last time where we talked about various guises of the mean value theorem. We began by discussing what's called the interior extremum theorem. Let I be an open interval from a to b and say that f is a function differentiable on I. First, assume that f attains its maximum value at some point p. That is, f of x is less than or equal to f of p for all x in our open interval I. Then f prime of p equals 0. Second, assume that f attains its minimum value at some point p in I. That is, f of x is greater than or equal to f of p for all x in the open interval. Then, similarly, f prime of p equals 0. As a corollary, we have Darbo's theorem. Let's say that I is a closed interval from a to b, and that f is differentiable on this closed interval. Assume that there exists some L such that f prime of A is less than L is less than f prime of B. Then there exists a point P such that P is in the interior, that is, P is between A and B but not equal to, and f prime of P equals L. This result is named after the French mathematician Jean-Gaston Darbo, and sometimes we say that the derivative has the intermediate value property. Next, we had Rolle's theorem. Say that I is a closed interval from a to b and denote I circle as its interior, that is the open interval from a to b. Say that f is continuous on the closed interval and differentiable on its interior. If f of a equals f of b, then there exists a point p in the interior such that f prime of p equals 0. This result is named after the French mathematician Michel Rolle. As a corollary, we have the mean value theorem. As before, let I be the closed interval from a to b and I circle be its interior as the open interval from a to b. Say that f is continuous on the closed interval and differentiable on the open interval. First, there exists a point p in the open interval such that f prime of p equals f of b minus f of a divided by b minus a. Second, f prime of p equals 0 for all points p in the interior if and only if f is a constant on the interior. We have a slight generalization of this, which we call the generalized mean value theorem. As before, let I be the closed interval from a to b, I circle be its interior as the open interval from a to b, but now say that f and g are two functions which are continuous on the closed interval, yet differentiable on the open interval. Then there exists a point p in the open interval such that f of b minus f of a times g prime of p equals g of b minus g of a times f prime of p. Let's now get into the concept of a nowhere differentiable function. To do so, let's recall a few concepts that we've discussed so far throughout this course. Previously, we found that there are functions which are everywhere continuous, and there are functions which are nowhere continuous. For example, any polynomial is a continuous function for any real number. Similarly, Dirichlet proved in 1829 that there is a function which is discontinuous at every real number. Indeed, consider that function f such that f of x is 1 whenever x is a rational number, but f of x is 0 whenever x is an irrational number. Then we found earlier in the course that this function is discontinuous for every real number. We also found that there are functions which are differentiable everywhere. Let's return to the polynomials again. Every polynomial is differentiable at every real number. And we found that differentiability implies continuity. That means on a closed interval I, if f is differentiable at a point p, then it must be continuous at a point p. This leads us to a couple of motivating questions. First, can we find a function which is continuous but not differentiable? Second, can we find a function which is nowhere differentiable? Well, these questions were first considered by the German mathematician Carl Weierstrass in 1872. In fact, he found a function f which is everywhere continuous but nowhere differentiable. This is the same Weierstrass that is attributed to the Bolzano-Weierstrass theorem. Let's now try to give a precise statement of what Weierstrass actually proved. Let a and b be two real numbers satisfying three properties. First, a is a real number between 0 and 1. B is a positive odd integer, such as 1, 3, 5, 7, and so forth. And a times b is greater than 1 plus 3/2 pi. Then the following function that you see as an infinite sum is well defined, continuous everywhere, but differentiable nowhere. Now, this is a rather strange looking sum, so let's maybe ask a motivating question for now that we'll come back to later. Why is this function well defined? And what does it mean to take an infinite sum? For now, let's take a look at a few examples of this function. We see that this is really the limit as we increase the number of terms in the sum. So let's consider these partial sums. That is, given any capital N, we'll write f sub n as just the sum of the first n plus 1 terms. So when n is equal to 1, we then have f sub 1 is 1 plus a cosine of b pi x. Let's consider a to be 1/2 and b to be 13. Then it satisfies the three conditions that we had on the previous slide. Here, let's zoom in to our function to see the plot as x is between roughly 0.455 and 0.468. You can see that this plot really does look like the plot of a cosine function. Now let's consider n is equal to 2. This will be the plot of f sub 2 of x, which is 1 plus a cosine b pi x plus a squared cosine of b squared pi x. You can see here that this really does look like it's an oscillating function, but it turns out that it's actually the sum of two cosines. Now let's take a look at the case when n is equal to 3. You can see here that we have a continuous function, but it seems to be oscillating quite wildly. This, of course, is because we have a sum, 1 plus a cosine bx plus a squared cosine b squared pi x plus a cubed times cosine b cubed pi x. Let's take a look at the next case when n is equal to 4. You can see here, still it's a continuous function, but it's starting to oscillate so wildly that really becomes questionable whether the function really is differentiable. And finally, let's take a look at the case when n is equal to 5. Hopefully now you can see the trend of what's happening more generally with this function. The function is still continuous, but it is oscillating so wildly now that we really don't expect the derivative at any point to exist. Here's a proposition that will help explain a little bit more why Weierstrass's theorem is true. Let's consider the same function f as on the previous slide, but now let's note that we can write f of x as a sum as lowercase n goes from 0 to infinity of 1 over b to the n alpha times cosine of b to the n times pi times x. Here, we'll let alpha be negative log of a over log of b. Recall that alpha is between 0 and 1, and beta is greater than 1, so alpha here must be a positive real number. The statement is that there exists a constant m such that in absolute value, f of x minus f of p is less than or equal to m times x minus p to the alpha for all x and p in the real numbers. Actually, this proposition really begs a larger definition. Let I be a closed interval. We'll say that a well-defined function f is Holder continuous if there exists constants m and alpha such that f of x minus f of p is less than m times x minus p to the alpha for all x and p in our closed interval. We actually have the following three statements that show that such functions are very special. First, if a function is Holder continuous for alpha equals to 1 if and only if it is a Lipschitz function. Second, f is whole or continuous for alpha greater than 1 if and only if it is a constant function. And finally, if f is whole or continuous, then f is uniformly continuous. But we've already seen that functions which are uniformly continuous must be continuous. So this shows that every whole or continuous function is actually an example of a continuous function. So using the proposition at the top of the slide here about Weierstrass's function, we actually see that it must be whole or continuous, and therefore this is what proves that this function is continuous everywhere. It is continuous for all real numbers. We're going to skip over the proof of why this function is not differentiable for any real number, but we will come back in a future lesson to discuss why such an infinite sum is well defined. Thanks very much for watching.